So as I said, we'll start today's session with a discussion of few of the questions from worksheet number 5, few of the trickier questions, and then we will move on to the basics of the second part of calculus, which is integration. So we'll start with question 1, few of the parts which are to do with calculation of domain and range. So let's start with the first part of question 1, where we had a function like this: y is equal to square root of 1 minus 2 sine x, I think, right? Okay, so let's understand domain and range. So as I said, that when the question does not give us any domain, that means we have to take the natural domain of the function. So what we mean by the natural domain of the function here is the values of x for which y is real. Okay. So basically by domain here, we mean we have to find the set of values of x for which y is defined as a real number. So here you can see y is defined as square root of something. So that means for y to be defined as a real number here, the quantity inside the square root must be a non-negative quantity, which means that sin x must be less than equal to half. So now we know that in general, sin x is between -1 and half. Okay. So that means over here, sin x will range between -1 and half. So we have to take the domain such that this happens. So basically the domain is the set of values such that this condition is satisfied. This -1 is not coming from any restriction of the domain. It is coming from the fact that sin x itself is a function which can never go below -1. No? So that means the quantity inside the square root here, it should be such that our term sin x should be less than equal to half. That means it will be ranging between -1 and half. Okay, Abhinav, this was the difficulty that you were having. Huh? Hope this is clear now. Okay. So now we want to, so how we'll find the values of x for which this happens. Now remember that sin x is a periodic function. Okay, so sin x is basic graph. Looks like this. If we plot sin x versus x. So in one fundamental cycle, looks like this. And then it repeats. Before also it's repeating. So, so generally speaking, sin x ranges between -1 and 1. But here we want it to be restricted to less than equal to half. So we don't want these values in between that are going beyond half. So you can see this point is pi by 6 and this point is 5 pi by 6. This okay. So 30 degrees or 150 degrees. So our domain should be which part basically? It should be this part. Okay. Then this part should not be there in the domain. Then this part. And then repetition of this everywhere. Okay. So for this condition to be satisfied now, we can see that in the fundamental cycle, x should belong to the interval 0 to pi by 6, a union with 5 pi by 6 to 2 pi, okay, in x belonging to 0 to 2 pi. So general solution, x will be 2n pi to 2n pi plus pi by 6, union with 2n pi plus 5 pi by 6 to okay, where n is 0 plus minus 1 plus minus 2. So this is our overall domain. This becomes our domain. So this is more about trigonometry really than anything else. Okay. Now, next thing, let's talk about range. So range is the set of values of y. So in this particular case, you can see y is equal to square root of some term. So y's minimum value is when sin x is maximum, which is basically half. So y's minimum value is 0. Whereas y's maximum value is for sin x's minimum value, which is -1. So y's maximum value is square root of 1 minus 2 into -1, square root of 3. So that means the range is between 0 and root 3. This is becoming our range. Whereas this here was the domain.
Sir, sir,
Yes.
sir, can you explain the domain part again?
Yeah, just go through it. I've explained it. So domain is that set of values of x for which y is real. So the quantity inside the square root should not become negative. So that's how we are getting that sin x should be less than half. So now we have to find those values of x for which sin x is less than half. So basically we have to remove those parts for which sin x is becoming greater than half. So that is between 30 and 150. So between 0 and 360 degrees, we can take all values of x other than between 30 and 150. So this becomes the domain in the fundamental cycle of 0 to 2 pi or 0 to 360. Then we have to just generalize the solution to the 2n pi form because it's a cyclical function.
Okay, sir.
Uh, Sir, instead of 2n plus 1 pi, it should be 2n pi. Na?
Okay, so hope this is clear. So I have sent you this solution, so should be able to go through this. Okay, let's move on to another part. Okay, next question we'll look at is question part 3 of question 1. Okay. So now here you can see that as far as domain is concerned, sin x is defined as a real value between -1 and +1 for all values of x, and so is cos x. So our domain will just become the set of all real values. Basically, all real number. There is no restriction on the domain whatsoever. Okay. Now the other thing is that sin x and cos x are individually periodic functions. With a cycle or period of 2 pi. So therefore here y will also be periodic. Okay. And again with a cycle of 2 pi. So therefore the global maximum or maximum value of y in entire domain, that will be equal to the local maxima within 0 to 2 pi. And likewise, the global minima will also be equal to the local minima. So this problem now gets converted for the range. It becomes converted to calculation of local maxima and minima. Okay, so therefore range will be between local minima and local maxima. Okay, so we just need to now find the local minima and maxima. So for local minima and maxima, remember you have this general process. Okay, dy by dx is cos x minus sin x. Okay. Second derivative is minus sin x minus cos x, or so this is our step one. Okay. Then put dy by dx equal to 0. Step 2 for critical points. If I take this domain, in that we can see that first and third quadrant. So these are our two critical points. And then we need to do the third step, which is the second derivative test. So at x equal to pi by 4, the value of d2y by dx square is equal to, now d2y by dx square is this. Substitute this here. So it is minus of sine pi by 4 plus cos pi by 4, which is a negative value. So that means there is local maxima at x equal to pi by 4. Similarly, at the second critical point, value of d2y by dx square is minus of sine 5 pi by 4 plus cos 5 pi by 4. So that is minus of minus 1 by root 2 minus 1 by root 2. So it's a positive value. So that is now showing us that there is a local minima at x equal to 5 pi by 4. Okay. So we have established now where the local maxima is, where the local minima is. Now we'll find the local maxima and minima. So therefore, local maxima at x equal to pi by 4 equals to the value of y at x equal to pi by 4. So the function, the original function we are talking about was sin x plus cos x. So it's the value of the function at pi by 4. So this is the local maxima's value. And similarly, this is the value of y at x equal to 5 pi by 4. So this is our local minima at this point. So that means now we know that y ranges between minus root 2 and root 2 for x belonging to this interval. Okay. Now, since y is periodic, okay, with a cycle of 2 pi, so therefore y's overall range is also this for x belonging to all real numbers. This now becomes our range. So because this is a periodic function we are dealing with, so here you can see our approach for calculation of range is different compared to the first one. Which had a broken domain. So
So can you scroll little up?
okay. Okay. Next, we'll move on to question 2, which is about local maxima and minima. We'll start with the second part of question 2. Now, this function has something peculiar in it, so we'll discuss. So we just want to find local maxima and minima. So here we need not bother about domain and range. Okay. But looking at the function, you can see one thing over here, that x should not be equal to 0 because we have a 1 by x squared term. Okay, so that's just one thing to observe over here. So anyway, let's start with local maxima and minima. So step 1, as we've seen, is calculation of derivative, which will be this, and second derivative, or which we have to differentiate this. So the second term's minus 2 into minus 3, that's plus 6 into x to the power minus 4, or like this. So this is our second derivative. Then the second step, we have to find the critical points. For that, we have to find the roots of the derivative. So here, what we can do is so this term we need not worry about because we have already taken x not equal to 0. So 1 by x cube term is never going to reach a value of 0 other than x tending to infinity. But this term x to the power 4 minus 1, we can first write it as x square minus 1 into x square plus 1 and further expand it as x minus 1 into x plus 1 into x square plus 1 is equal to 0. So this 1 by x cube will not be 0 other than x tending to infinity. X square plus 1 is never 0. So it's either of these two terms. So we get two roots for this equation, x equal to 1 and x equal to minus 1. So these are our critical points. Okay. Now when we do the second derivative test here, we see something interesting, that the second derivative is positive for both the values. That means both of them are local minimas, which might seem like a strange thing, okay, but we'll understand why is that happening here. So at x equal to 1, we are having a local minima, and at x equal to minus 1 also,
It is again positive.
we are again having a local minima. So now we can see that local minima at x equal to 1 is equal to the value of the function at x equal to 1. The function, remember, was this, okay, and the local minima at x equal to minus 1 equals to the value of the function at minus 1. Which is also equal to 2. Okay. So finally, our answer becomes that for this function, okay, local maxima does not exist. There is no peak point in the graph, that means, okay. Whereas local minima is equal to 2 at x equal to 1 and again at x equal to minus 1. So there's a repeated local minima of 2 at these two positions. So this might seem like a very odd result finally, that how can a graph have two dips without having any peak point? But we'll understand that also with some further explanation. Okay, this is a very unique type of function where this kind of situation happens, and we'll discuss in a minute. But just go through these steps first. Okay, now let's try to understand the logic of why this happens. So as far as the question is concerned, this is done. Okay, this is enough. Okay, but again, if we try to understand the behavior of this function, we can see that the domain is like this. Okay, and the derivative of the function so if we see this function, it has a very interesting behavior that y tends to infinity for x tending to 0, because there's a 1 by x squared term. Of course, it's not defined at x equal to 0. So 0 is excluded from the domain. We can see that y also tends to infinity for x tending to either plus infinity or minus infinity, because there's the x squared term. Okay. And y is equal to 2, which is the local minima at x equal to both plus and minus 1. So if we think of a sort of number line analysis, now in terms of number line analysis, we can see like this, that 0 is a point which is removed from the domain. Okay. But other than that, the significant points are minus 1 and 1, where there is a local minima equal to 2. Okay. And then the function is increasing, going towards infinity, increasing, going towards infinity. Like this. So this shows us the behavior of the function, and we can even now, understanding the detailed behavior, we can even visualize a reasonably accurate graph of the function. So the graph of the function will be something like this. So that is how you can see that what's happening for this function is that we have two local minimas, which are, by the way, also global minimas. So you can see the domain of this function is the set of all real numbers excluding the point 0, and the range of the function is 2 to infinity. And local minima equals to 2 at x equal to plus minus 1, whereas global minima we've already seen as 2. Okay. Whereas local maxima does not exist. There is no peak point. So this is the strange behavior of this function, because it has this discontinuity. So it's a function's graph where it is possible that there are two dip points without any peak points.
So can global maxima exist?
Sorry?
Can global maxima exist in this
Yeah,
condition?
global maxima is there. No? We have shown in the range that is going from 2 to infinity. So the upper limit of y itself is the global maxima. No? So global maxima is tending to infinity. Understood now?
Yes, sir.
Yeah. Okay, let's move on to another part of this. Third part of this question is also a little bit tricky, so let's discuss that. It's not really tricky. What I'd say is that the steps are lengthy in this. So anyway, we want to find local maxima and minima. So we won't worry about domain and range. Okay. Even though actually what we'll see is again the domain is unrestricted. It's defined for all values of x which are real. And the range will actually be the range between the local and minima and maxima because the function is periodic. Okay, so indirectly by calculating local maxima and minima, we're actually calculating the global maxima and minima or the range from that. Okay, so anyhow, so step one, differentiate this function. So differentiation of cos x will become minus 2 cos x sin x, and differentiation of cos x is minus sin x. So we can also write this as minus 2 sin, sorry, minus sin 2x plus sin x. So second derivative, we can just differentiate this term, it will be easier. So it will become minus 2 cos 2x plus cos x. So that's our first step done. Now critical points. So for that, to find the roots of this equation, take sin x common. Let's see. Okay. So from here we see, yeah.
In d2y upon dx square, we will have only cos minus cos 2x plus cos x.
Yeah, differentiate this now. Differentiate this term. So derivative of minus sin 2x will be what? Minus cos 2x into differentiation of 2x, which is 2.
Okay.
Understood? So instead of using the product rule for this, now I have differentiated this. This is equivalent to this, right? Okay. So this means that either sin x is equal to 0 or 1 minus 2 cos x is equal to 0. So sin x is 0 will give us 2 roots in the fundamental cycle, and cos x is equal to half will give us again 2 roots, pi by 3, that is 60 degrees, and in fourth quadrant 2 pi minus pi by 3, so that is 5 pi by 3. So that is 60 degrees and 300 degrees. So we have 4 critical points in 0 to 2 pi. Okay. So in other cycles, it can repeat itself. So general solution will become this. Two n pi plus pi by 3. So anyhow, we will consider only the 4 critical points in one cycle of 0 to 2 pi. and we'll understand the rest is repeated, so we don't need to worry about that. Okay. So step 3, second derivative test. Okay. So let's start with the first one. At x equal to 0, the second derivative's value is how much? Now see, this is the second derivative, so it is minus 2 cos 0 plus cos 0. So that's a negative value. It's minus 1. So we have a local maxima at x equal to 0. Okay. Then at x equal to pi by 3, the second derivative's value is minus 2 cos 2x. So 2 pi by 3, okay, plus cos pi by 3. So that, as you can see, will become positive. Cos 2 pi by 3, that's cos 120. So that's minus half. So minus half into minus 2 will give us 1. And cos pi by 3 or cos 60 is half. You can see it's positive value. So we will have a local minima at x equal to pi by 3. Okay. So like that, if you continue the analysis, you will see that you will get again local maxima at 5 pi by 3 and again local minima at you will get local maxima at pi and then again local minima at 5 pi by 3. Okay. So if you take these critical points sequentially, that is from smaller to larger, there's 0, pi by 3, pi, and 5 pi by 3. So just make sure you've understood these steps and do the same thing, second derivative test at x equal to pi next, going sequentially, okay, and then 5 pi by 3, because this is these are the critical points. So you'll see going sequentially, we'll again get local maxima and local minima. Okay, so let's complete the analysis. So at pi, you can see that it's rather easy. Minus 2 cos 2x. So that will become 2 pi plus cos x. There's cos pi. So that will become minus 2 into 1. So that's minus 2 plus cos pi, which is minus 1. So it's a negative value. So again, you can see you'll get a local maxima at x equal to pi. And the final point at x equal to 5 pi by 3. Get minus 2 cos 2x. So that is 10 pi by 3 plus cos x. So that is 5 pi by 3. Okay. Now let's look at this quantity. 10 pi by 3 we can write as 9 plus 1 pi by 3. So that is 3 pi plus pi by 3. That is 2 pi plus pi by 3. Okay. So you can see that cos 10 pi by 3 is equal to cos of 2 pi plus pi by 3, which is cos of pi plus pi by 3, which is minus cos pi by 3, which is basically minus half. So this becomes minus 2 into minus half, which becomes 1 plus cos 5 pi by 3, which we've already seen as half. So this is again a positive value. So again, we are getting local minima at x equal to 5 pi by 3. So again, like this is a rigorous exercise in trigonometry for us. Okay. So you might feel that at this stage it's too lengthy and tricky, but the thing is, we will see that there are some future chapters in physics like oscillations and simple harmonic motion, etc. We need to understand quite a detailed analysis of the basic trigonometric functions like sine, cos, sine square, the combination of these kind of terms, etc. So it's going to be helpful for our future analysis in physics to be able to do these kind of detailed and tricky analysis in trigonometric functions, which is why I have included a few of these questions here. Don't worry that they're lengthy and it's taking time to solve and all that. It is for your learning purpose more than anything else. It will help you in trigonometry also. It will help you in physics also. So now what we have got is that we are having local maximas at which points? At these 2 points. X equal to 0, x equal to pi. Okay. So generally speaking, 2n pi and we are having local minimas at x equal to pi by 3 and x equal to 5 pi by 3. And similarly, we can develop a general solution. So what is the value of the local maximus? Okay, so that is the y coordinate at x equal to 0. So remember what was y? Y was cos square x minus cos x. Okay. So that is equal to cos square 0 minus cos 0, which is 0. So we have a local maxima equal to 0 at x equal to 0. Then at x equal to pi, it becomes cos square pi minus cos pi, which is 1 minus of minus 1. So that is 2. So we have another local maxima which is equal to 2 at x equal to pi. So these are the two local maximas. Whereas let's analyze the two local minimas. So local minima equals to minus 1 by 4 at x equal to pi by 3. And again, 5 pi by 3, you will see it repeats its value. So local minima is having a repeated value at both the points. Whereas local maxima was having two separate values, which means that the graph of this function is going to be quite interesting. We'll discuss. Okay. But our answer is complete over here. We have found out the local maximas and minimas. So these four are the answers. Two local maximas, two local minimas. Okay, so if we now analyze the graph of this function, we will come across that one. Okay, let me explain. See, what was happening here is the function originally was cos square x minus cos x, right? So the derivative you understood now how it has come. This step is clear, beta? Yes, this step is clear.
Yes, sir, I got it.
Okay, now the next thing is we have to differentiate this now.
Yes, so we'll apply the product rule.
But see, instead of applying the product rule, you can also use the fact that this term 2 sin x cos x is sin 2x, is equivalent to that. So we can also write this as minus sin 2x plus sin x now. So for second derivative, we can differentiate, instead of differentiating this term, we can differentiate this whole term. Understood now?
Yes, sir.
So when you differentiate this term, the first term is differentiation of minus sign, so that is minus cos, but 2x. So there'll be a chain rule. So there'll be a multiplied by 2. Got it now?
Yes, sir, got it.
And differentiation of second term is cos x. So that's how we are getting minus 2 cos 2x plus cos x. That is how we are getting the second derivative as this. Okay, so you can also do it by the product rule and it will come to this, but it will be lengthier. Got it now?
Yes, sir.
Okay. So now coming back to putting these things together here, the maxima, minima. Okay. So though the question is completed, but we can also understand how it's a very interesting graph that will result in this. So if you look at the graph of this function in one fundamental cycle of 0 to 2 pi, you'll see it has this interesting kind of behavior. Say this is the value 2, and let's say this is the value minus 1 by 4. So it is having a local maxima of 0 at the point x equal to 0. So it's like this. Okay. Then it's coming down to minus 1 by 4 at pi by 3. You can see. Then it's going all the way up to 2 at pi. Then it's again coming back to minus 1 by 4 at 5 pi by 3. And then this whole cycle will repeat itself. So from here onwards, the graph will repeat itself. Before this, it would have repeated itself. So, in every cycle, it has 2 dip points and 2 peak points. But the peak points are having different values, 0 and 2, again 0 and 2, again 0 and 2. Whereas the dip points are having a common value of minus 1 by 4. So this is the information that we are getting from the concept of local maxima and minima of this function. Okay. Okay, now one more question I want to do of the local maxima and minima set. Okay, before we move on to integration. There is one slightly lengthy type of question. Yeah, the fourth question of this same one. So this is again a question which will require a lot of patience in differentiation, because you'll have to use the quotient rule repeatedly. So when we are executing the differentiation part, you'll have to use this formula that differentiation of a quotient is denominator into differential of numerator minus numerator into differential of denominator divided by denominator squared. So let's apply that. Okay. So denominator, that is this term, multiplied by differentiation of numerator, which is 1, because numerator is x, okay, minus numerator, which is x, into differentiation of this term. So you'll have to use chain rule, 1 plus x squared to the power 3 by 2. So anything to the power 3 by 2 has a differentiation of 3 by 2 into that to the power half into differentiation of this term, that is 2x. Okay. Whole thing divided by 1 plus x square power 3 by 2 whole square. So that becomes 1 plus x square to the power 3. Okay. So now if you simplify this, you can see this is 1 plus x square to the power 3 by 2 minus 3x square, okay, into 1 plus x square to the power half divided by 1 plus x square to the power 3. So we can take square root of 1 plus x square common in the numerator. So we'll be left with 1 plus x square term here minus 3x square. Okay. So again, we can see this and this, we can cancel out some of the values. Okay. And this term will become 1 plus x square minus 3x square. So 1 minus 2x square. And absorbing this term within the denominator. So the denominator's power will become 3 minus half. Okay. So that is 5 by 2. So this is our derivative. Okay. So the critical points will come by putting this as 0. But before that, we have to also find the second derivative. So similar kind of steps for second derivative. Denominator into differentiation of numerator. So that is minus 4x. Okay. Minus numerator into differentiation of this term, denominator. So that's power 5 by 2. Okay. This upon denominator whole squared. So similar kind of patience we have to do this also. So minus 4x into 1 plus x square to the power 5 by 2. So it will become minus, this 2 and 2 will cancel. Okay. So we have 5x, okay, into 1 minus 2x square into 1 plus x square to the power 3 by 2. So again, in the numerator, we can take 1 plus x square to the power 3 by 2 common. Okay, so this term will give us this, okay, and this term will leave us with just this. So again, readjusting. So you can see we have minus 4x minus 5x. So minus 9x. Okay. and minus 4x cube plus 10x cube. So plus 6x cube. Okay. This term you can absorb with the denominator. So the power in the denominator will become 5 minus 3 by 2. So that is 7 by 2. So our second derivative will also become this type of a term. Okay. 3x common. So we have 2x square minus 3. Okay. So this was a lengthy part. The rest of the question is going to be straightforward. Critical points and second derivative test is going to be simple enough. The critical thing in this was having the patience to differentiate properly, okay, correctly, using the quotient rule twice in this kind of a monster expression. So again, this is the kind of patience and accuracy that you require in certain types of problems. Okay. So just go through this once and now work out the critical points and second derivative test yourself if you're finished with this. Okay, so now let's complete the calculation of the critical points in second derivative test. Now you can see in this the denominator is never going to be 0 because it's 1 plus x squared to some power. So it's, 1 upon denominator is never going to be 0. So basically we are solving for this. So we are getting these two as critical points. Okay. And when we substitute this in the second derivative, we will see that d2y by dx square for this term will come out to be negative, whereas d2y by dx square for this term will come out to be positive. So I'm not doing the full calculation. You can just substitute these here or here, whatever. Okay. So you'll find it easy enough to see why they become negative and positive. So we'll have local maxima at x equal to 1 by root 2, and we'll have local minima at x equal to minus 1 by root 2. So this is that general type of function where you have two critical points. One of them is a peak point, one of them is a dip point. So the value of the local maxima will be the value of the function at 1 by root 2. Remember, the function was this. So when you put the value of x in this as 1 by root 2, you will get it as 2 by 3 root 3. And you put this, you will get the value as minus 2 by 3 root 3. So this is the local maxima, this is the local minima. Okay, so as I said, the rest of the steps were easy in this. It was just the differentiation that was quite lengthy. Okay, so now rest of the questions, I think you will be able to handle in this worksheet. If you just go through the hints and solutions that I've sent. However, if any doubts still remain, then we will discuss again in the next lecture. So at this stage, we'll move on from here to the next part of calculus, which is integration or integral calculus. Now we will find this in general easier to handle because we're already familiar with one part of calculus. So that is definitely going to help us in our understanding of the second part, which is integral calculus. So in integral calculus, there are two types of operations. Okay. So the first type of operation is called indefinite integration. And the second is called definite integration. So let's understand each of these operations. Indefinite integration, it is an operation that applies to a function which applied to a function results in the calculation of its antiderivative. So let's understand the meaning of the term antiderivative. So for a given function, let's say fx, the antiderivative, which we can denote with the symbol ix, because it comes from integration, is such that the derivative of ix is equal to fx. So it's anti of derivative. It's a function. The operation on fx gives us such a value that its derivative should be equal to fx. So that is the meaning of the term antiderivative. So we can also visualize the relationship between a function and its antiderivative like this, that if we differentiate this, it gives us this. Whereas if we integrate this, it gives us this. So for example, we know that 2x is the derivative of x square plus c, where c is any constant. So therefore we can say that x square plus c is the antiderivative of 2x, or cos x is derivative of sin x. So that means sin x is antiderivative of cos x. Okay, so just make a brief note of this definition of antiderivative, then we'll continue further. So that's why we'll see that it's very easy to understand integration, because it's just a reverse process of differentiation. Okay, next thing we'll understand the symbol of integration or indefinite integration. This is the symbol used for indefinite integration. Okay. So how we applied it to a function is the integration symbol followed by the function followed by the term dx. Okay, so this whole thing, it is now read as the operation of indefinite integration of the function fx, okay, with respect to the variable x. Okay. So this symbol shows us what operation we are doing. We are doing integration. Then the next thing written next to it is the function itself that we are integrating. And the dx shows us that we are integrating the function with respect to the variable x. Okay. So for example, okay, this is indefinite integration of x square plus 5x, which is a function with respect to the variable x. Okay. Or okay, this is indefinite integration of the function e raised by t with respect to the variable t. Or if we write something like this, let's say a dt. Here it is understood that a should be a function of t, okay, because a is being integrated with respect to t. Now what this operation results in, this operation results in the antiderivative. So the output that this operation gives us is the antiderivative of fx. So this is the meaning of the operation. What it gives us the antiderivative.
Sir, can you please explain the antiderivative e raised to t dt?
We'll come to that. We'll learn what that is. Okay. But what the symbol means, it is integration of e raised by t with respect to the variable t. We'll learn all this, how to integrate x square, we'll learn how to integrate 5x, how to integrate e raised by t with respect to t, or e raised by x with respect to x. All those will come from formulae, just like we have done formulae for differentiation. Like that, we'll have some standard formulae and standard properties of integration. Okay. So far we've just seen that what is the definition of integration, and what it gives us, the output it gives us is the antiderivative. Okay, now one is we can do integration by a bit of guesswork. Okay, but that will not always work. So for example, if I'm integrating 3x square, okay, so this should give me what? So this basically tells me that if the function is 3x square, then what should be the antiderivative? So that I know that differentiation of ix should give me fx. Now you all know that 3x square is differentiation of what? X cube. Okay, so it's pure observation that the differentiation of x cube is 3x square. Okay, but also the differentiation of x cube plus 1 is 3x square, or the differentiation of x cube minus root 2 is also 3x square, or in general the differentiation of x cube plus any constant is equal to 3x square. So therefore, what is the conclusion here? That antiderivative of 3x square should be equal to x cube plus c. So that should tell us that, okay, integration of 3x square should be equal to x cube plus c. So this is more or less by guesswork, you can say. We have come to this conclusion by observation or basic guesswork. I mean, it's not a total fluke guess, okay, but it's a sort of calculated guesswork. Okay. But now, based on this kind of formula of differentiation that we know now, we can develop some formula of integration. So see, we know that differentiation of x to the power n is nx to the power n minus 1. Okay. So we can say that x to the power n minus 1 is the differentiation of x to the power n upon n. Okay. Or we can say that x to the power n is differentiation of x to the power n plus 1 upon n plus 1. Okay. Or in general, x to the power n is differentiation of x to the power n plus 1 upon n plus 1 plus c. Okay. We can further understand this with some examples. Okay. So for example, differentiation of x cube we just saw is 3x square. So that means x square can be written as differentiation of x cube by 3. Okay. Differentiation of x to the power 5 is 5x to the power 4. So that means x to the power 4 is the antiderivative of, I mean, x to the power 5 by 5 is the antiderivative of this. Okay. We know that differentiation of x to the power half is to the power minus half. So that means x to the power minus half can be written as differentiation of x to the power half divided by half. So all of these examples you can see, they fit this formula. Okay. And adding the constant makes no difference because you know differentiation of a constant is 0. So from this formula now, we can develop the general formula of integration, that integration of x to the power n is equal to x to the power n plus 1 upon n plus 1 plus c. Where c is called the constant of integration, okay, and can be any real number. In fact, that is why this operation is called indefinite integration, because the output it gives us is not a definite function. It has an indefinite term, which is a constant of integration, which can take any real value. Okay, so just make a note of this, people. And while you're making a note of it, make sure you understand the 3 examples I've put on the side here. Okay, so let us look at some examples of the application of this. Yeah, n can be any real number in this. So other than n equal to -1. So in this formula, integration of x to the power n dx is x to the power n plus 1 upon n plus 1 plus c. N can be any real number excluding n equal to -1. So for -1, we have a separate formula we'll discuss, because if we take n as -1 on the right hand side, we get an undefined quantity because n plus 1 in the denominator becomes 0. Okay. So let's look at an example. Integration of x square will just become x cubed by 3 plus c. Integration of, let's say, 1 by root x will become x to the power minus half plus 1 upon minus half plus 1 plus c. So that will become
But
2 root x. Yes.
even if we don't consider n plus 1 as a denominator, we will get the same answer, right? Means when we uh, when we differentiate x cube, we will also get the 2x square.
No, that will not be correct, beta. That's why the formula is then n plus 1. You see, you differentiate x cube. What you get? You get 3x square. But what is the quantity? It's x square, no? So the 3 has to be there in the denominator.
Okay.
Only then we'll get x to the power n, no? So that n plus 1 is essential in the denominator. So this is the integration step. This is the integration step. We'll discuss next about what happens if n is equal to -1. But these are basic examples of any real number values of n other than -1. So you can understand that it's just the reverse process of differentiation. Differentiation of x to the power n, you multiply by a factor of n and the power is reduced by 1. Here we divide by a factor of n plus 1 and increase the power by 1. So it's like an inverse operation of differentiation. Okay, now let us see the exception for n equal to -1. Now we know that differentiation of natural log of x is 1 by x. Okay. So therefore integration of 1 by x is natural log of x plus. So this formula you remember as the exception case of x to the power n, where n is equal to -1. So that formula applies everywhere except for x n equal to -1, where instead of that formula we use this integration. Okay. So now other than this we have some basic properties of integration. Now these are very similar to the properties we have learned about differentiation before. So the integration of any constant becomes a linear function. Okay. So for example, integration of 10 will be 10x plus c. Then second thing is integration of a constant multiplied by a function. The constant can be brought outside the operation. So it is the constant times integration of that function. Okay. So k is any constant here also. So for example, if we are integrating 5x square, so that will become 5 times integration of x square. So that will become 5 into plus c, of course. Okay. This will become the answer. So this is pretty logical stuff. Okay. And the third and final property, the distributive property, the integration of sum of two functions or difference of two functions is in sum of their integrations or difference of their integrations. So for example, if we are integrating this. We will write the constant in a combined form. There are two integrations, so there's technically two constants, but there's some will be written as a combined constant, which can take any real number value. So with the help of the x to the power n formula and these three basic properties, you can see you can differentiate any and every algebraic type of function, polynomials included. So simple functions can be integrated by using this method. Okay. So you can get started on integration. I will send you a basic worksheet based on these formulae also, okay, for this week. Next week, we will look at more complex applications of indefinite integration and also definite integration. Okay, so hope all this is clear, and with this, we conclude today's lecture.
Sir,
So wish you all the best, and that's it for today's session. Thanks for attending.
Sir,
sir, am I audible? Sir, am I audible?
should we leave the lecture?